Okay, the review sheet. This first one here is a bit of a trick question. What is the mass of an 80 kilogram person on this planet? Well, it's just 80 kilograms, right? There's no calculation. The mass is mass. It doesn't change no matter where you go. There's no calculation to be done. For this one, what is the weight of an 80 kilogram person on this planet? Well, that's Fg equals mg, all right? So it's 80 kilograms, but it's 4.5 times Earth's gravity of 9.8 newtons per kilogram. So you gotta multiply the g by 4.5. So plug it into our calculator here. We've got 80 times 4.5 times 9.8. That gives us about 3,528 newtons of weight. Okay? All right. Frictional one here, piece of dry ice with a mass of 40 kilograms on a smooth surface. It's coefficient static friction. Okay. Weight of the block of dry ice. Well, let me just draw a force diagram over here. We've got Fn, Fg, we've got some kind of applied force, and we've got some kind of force of friction. Okay. So, weight of the block of dry ice, that's Fg, 40 kilograms times about 10 or 9.8 newtons per kilogram. I'm just doing the same calculation here, mg, 40 times 9.8. You get about 392 newtons. Or if you use 10, you'd get 400 newtons. Either way is fine. Okay, determine the amount of force required to get the block of dry ice moving. All right, so that's going to be the force of friction static. Alright, so it's going to be the static coefficient times the normal force. So it's a 0.021 times normal force, which has got to be 392 newtons, right? Because Fn and Fg have to be equal and opposite to each other. Alright, so 0.021 times 392 is 8.2 newtons. So that's how much force it would take to break it free. Keep it moving, that would be force of friction kinetic. That would be mu sub k times Fn. Same exact calculation, but you use the smaller number, the kinetic coefficient. Alright, so 0.018 times 392 equals 7.1 newtons. Okay, so 0.82 to break it free, 0.71 to keep it sliding. Very good. All right, on to the back. Force diagram for this box, moving at a constant speed. That's the key, right? You're going to have Fn and Fg, right? They have to be equal to each other. So try to make those arrows about the same length and do such a good job there. All right, it's Fg, Fn. We have an applied force, I'll call it Fa, or push, whatever you want to call it, and then we have a force of friction. And since it's moving at a constant speed, those two forces have to be the same, the applied force and the frictional force. The only variation in this problem you might have is if it was accelerating, then whatever direction it's accelerating in, that arrow has to be clearly longer. Toy car with a mass of 0.2 kilograms is propelled by a force from a spring mechanism with a strength of 0.8 newtons. Determine the acceleration of the car. All right, so we've got some toy car. There's some sort of F pushing it forward of 0.80 newtons. All right, it's going to have Fn and Fg. Those don't really matter. Acceleration is F net over the mass. All right. So F net equals ma, divide both sides by the m. So A equals 0.80 newtons divided by 0.20 kilograms. You get 4.0 meters per second squared for the acceleration. Newtons per kilogram is equivalent to meters per second squared. So how fast will the toy car be moving if the spring acts on the car for 1.5 seconds? So if that's how much it would accelerate each second, how fast would it be after 1.5 seconds? Well, it's got to be at least 4 meters per second. Well, let's see. Acceleration is change in velocity over time. We're looking for the change in velocity here. Multiply both sides by t. you get change of velocity, acceleration times time. So the change of velocity is 4.0 meters per second squared times 1.5 seconds. And that's going to be a change in velocity of 6.0 meters per second. Great. So final velocity, 6.0 meters per second. How far will the car move in this time? Well, delta x equals average velocity times time. Average velocity here is going to be the initial velocity plus the final velocity divided by 2. So the average velocity is 3 meters per second. So put that in over here, 3 meters per second times the time, which is 1.5 seconds. Delta x, 3 times 1.5 is 5.5. That's just before I, oops, or 4.5, sorry. What am I saying? 4.5 meters, the seconds cancel. So pretty straightforward. You could have also used El Grande for this if you wanted to. Either way would have been fine.